Hello, I'm Laura Cassidy from the American Chemical Society. Welcome to this news briefing from the American Chemical Society Spring 2019 National Meeting in Orlando. We're joined today by Dr. Julia Cornfield at the California Institute of Technology. She's studying polymers that could minimize fuel explosions and fires from accidents and terrorist acts. Dr. Cornfield?
Thank you. It's my pleasure to tell you about research that is, of course, not just me. So one of the first things I wanted to do is introduce you to some very important people. Jeremy Way, who's in the blue check shirt there, is the chemist who figured out how to make these molecules. Simon Jones, to the left, is acting as the head of a startup company that's trying to bring this to market. And then the tall fellow in the back is Jason Whaley, who's our lead contact with the investor, Rhapsody Venture Partners. And the startup is called Fluid Efficiency. Next. So the concept of mega supramolecules is to develop robust molecules that you can put in at a low concentration and benefit a wide range of fluid properties. So some of the applications include enhancing lubricants, potentially reducing the number of changes of an oil or a hydraulic fluid that are required, so it's environmentally nicer. And the one that I am the most passionate about is for use in fuel, where by inhibiting the formation of mist when you have a vehicle crash in ground transportation, an IED detonated under a fuel tank, or a plane crash, or a deliberate act of terror, you form fine mist of droplets. I'll say more about that. And if you can prevent that step, you can prevent the extremely hot fire that results and save lives. I'll tell you about some examples where people would have otherwise walked away if it wasn't for the fuel fire. So the key idea in reducing the risk of fuel fires is to control the droplet size. So in a scenario where you have a crash at highway speed or at aviation speed, the typical droplet sizes of the fuel are 5 to 10 microns. So 10 microns is the size of a red blood cell. So it generates a tremendous amount of interfacial area, and it mixes the fuel with air. And so you've got a very dangerous situation, and because of the large interfacial area, there's a higher concentration of organic vapor that develops before the crash has resolved. So during any crash scenario, you have hot surfaces, you have sparks, you have ignition sources. And if the amount of vapor is sufficiently high, then when you ignite the vapor, it provides the energy to essentially boil the rest of the fuel. And that allows you to essentially release almost all the energy of the fuel until you run out of either oxygen or organic. If you shift the drop size to larger drop sizes, so 80 to 100 microns, so to your eye it still looks like a mist, so the width of a human hair is 100 microns. Nevertheless, the interfacial area where the fuel vaporizes has been reduced by a factor of 100. And that smaller amount of vapor that escapes means that even though it ignites, so again, you still have hot surfaces, you have sparks, it ignites, it consumes all the vaporized fuel, and the rest falls down like rain. So it dramatically changes the outcome of that very first mist fire. And in the event where you have the very fine drops, temperatures in the case of a plane accident can reach the point that they melt the fuselage, right? Here, if you have the fuel falls down like rain, even if it ignites, it's a pool fire, which gives firefighters a chance, and it allows people to escape. It doesn't get as hot as fast, and so you have a much better chance to survive. So the key idea of these molecules is that they can act like, they can pretend to be an ultra-long linear chain. Now, since the 1960s, it's been known that if you have a very, very long, flexible chain and you put it in a fuel, it can have very mild effects under regular pumping and use. But in the event of an elongational flow, they'll go from being a random coil that's very small to stretching out to being thousands of times longer. And in that process, they take up a lot of energy. So you can imagine if you have wind going over a big drop of fuel and breaking it into a thread, and then that breaks up into drops, the molecules are in there saying, I don't want to stretch. And so the thread of fluid stays wider. And at the time it breaks up, if it's 100 microns diameter, you get drops that are about 100 microns in size. So the special thing about these very long molecules is they can be these compact random coils that don't interfere when they're just resting. And they have a latent ability to suddenly spring into action precisely when you need them to. Here's the problem. Those very long molecules, if you have them going through a filter or a pipeline, they're so long that they build up a very high amount of stretch in the middle, even in just a conventional turbulent pipeline flow. And that tension gets higher than the strength to break a covalent bond. Pop, they break. And it's irreversible. So that's the lower row there. So the molecules degrade irreversibly. And once they're down to molecular weights of a few 100,000, they bring no benefit at all, right? So the molecules we have pretend to be ultra long. So imagine you've got these long flexible molecules with a little bit of molecular Velcro that hooks them together right at the ends. And so they spend most of their life as a random coil. They're floating around doing nothing. And then when there's a strong extension, they stretch out. And then they say, oop, the tension got too high. Pop. So they can stretch to about 95% of the total extended length. So you get a lot of the benefit of them stretching. But when it gets critical, they let go. And so we can build in this molecular Velcro that will let go at a force that's 1/3 as big as you would need to break a covalent bond. So Jeremy, the chemist who figured out how to make them, he says, it's like you'd put a safety pressure relief valve on a tank. These are just tension relief valves in my molecules. Cool? And so that's how they avoid being irreversibly damaged. They volunteer to be transiently damaged, and then they just put themselves back together. Good. In terms of the timeline, these molecules were first reported in 2015, which seems like a blink of an eye, not very long ago. And that occurred in the journal Science because they were looking for stories where a theoretical prediction led to an experiment that proved a new concept. And so they picked our story to go in that journal. And that was very nice. It got a lot of attention worldwide. And that brought us in contact with people from industry, which also taught us more about how to bring this product to market. And led to the creation of the startup company, Fluid Efficiency. And they are right at the cusp of ramping up to being able to make hundreds of thousands of pounds a year within this year. And they're working with industrial partners who already make things on a very big scale, so that this little tiny company won't be the one that's actually responsible for that. They'll be working with a partner who knows how to make molecules at a very large scale and distribute them around the world. And so that's the exciting thing, I guess, about today, is that I get to tell you this story right as it's transitioning into a stage where we're working with major multinational companies, and hopefully it'll be spinning off products within the next year or two. Yeah. Great. And then I wanted to get back to the contact information. So if you have any questions afterward, or you just want the perspective of other people. So Simon Jones is the Chief Operating Officer in Fluid Efficiency, and his number is there. And if you'd like, he can introduce you to Jeremy Way, again, the chemist who figured out how to make these molecules. And Jason Whaley actually said he's got business in Orlando tomorrow, so if you'd like to be introduced, please let me know. And I can also give you his phone number if you need it. But I'd say the main additional perspective, different from an academic researcher, which is me, would be Simon Jones. He could answer questions about how far they're getting into scale-up and so on. Great.
Thank you, Dr. Cornfield. Are there any questions? Please state your name and affiliation before asking your question.
Hi, Charles Berquist, Science Friday. I'm not familiar with the scale at which these things happen. So do these molecules affect say, the vaporization that's going on inside a fuel injector into an engine or something like that?
Right. So we've only done one engine test. It was with diesel fuel in the type of engine that's used in a long-haul diesel truck. And the measurements were performed at UC Riverside, so independent. And they are well known for air quality related measurements. So they measured not only the fuel consumption and power output, but all the criteria pollutants. And we were very surprised to see that there was no adverse effect, no measurable effect at all on power output, fuel consumption, nor on all but 2 of the criteria pollutants. Most of them were indistinguishable. There was a small adverse effect on oxides of nitrogen, about 1.3%. The most remarkable thing to us was that diesel soot was reduced 12%. And in the US, we take it for granted that diesel soot is controlled, but we spend a lot of money on those pieces of equipment on each and every truck, and they actually consume a fair amount of the energy that's used by that truck. Most of the world does not have the benefit of that equipment. It's expensive both to install and to use. So in India and China, where they have serious air pollution problems that are more severe than we're suffering in the US at the moment, they would benefit from having something in the fuel itself because they don't have that soot control equipment. So there's a long way to go. So with engine tests, you need to get into things that run for 10,000 hours, and they dismantle the engine, check all the parts. And so we've still got a long way to go, but we were very pleased that it doesn't prevent atomization in the engine. Yeah.
Hi, so it's Kath O'Driscoll from Chemistry and Industry magazine. I just wanted to be clear on, were the ultra-long polymers, even though they weren't great, were they ever commercialized?
They're commercialized in other applications, but not in fuel. So for example, with paints and inks, you can use them to control the drop size as well.
Okay.
Yeah? So there are applications where they don't have to go through a long pipeline, don't have to go through filters many times. So it's like you put them in and then you use the product. So yeah.
And also, just to ask, if your supramolecular systems had been around, say at the time of 9/11, would you have expected to see lesser damage? I mean, how would you have expected to have seen, the outcome?
So this is actually my deepest motivation, is from 9/11. And the comments that I'm making are speculative, but they're based on a study that was done by the National Institutes of Science and Technology. In the US, there are fire experts. So whenever there's a major fire, especially if there's a loss of life, they're the ones that we call in to analyze what happened here. They found that it's actually quite difficult to create circumstances that would soften steel in a high-rise building. So the good news is it's very unlikely to see high-rise buildings collapse like that. What happened in those first few seconds is that the mist created by the fuel ignited, and it was either a deflagration or an explosion. It blew out hundreds of windows. High-rise buildings are sealed by those windows to prevent fires from having that much oxygen. Blowing out hundreds of windows is a big problem for controlling a fire. They also analyzed the images and found that the concrete that separates different floors had been ruptured. So high-rise buildings are designed so that you don't have combustion of contents on more than one floor at once. Okay? Then probably the most devastating is if you watch the video footage. So the airplane's coming in this way. It's striking concrete. It's pulverizing that concrete. Going back in the direction from which it came, even though there's air still rushing in, you see concrete flying out at highway speeds, right? So that concrete, it's like this, chunks of gravel being thrown at highway speed out in all the directions. Unseen by us, all the steel beams in a high-rise building are covered with a layer of insulation. It's, I think it was a 1/2 inch thick in the older tower and 1.5 inches thick in the newer of the 2 towers. It prevents the radiation from a fire from transferring that energy directly to the steel. Bare exposed steel heats up much faster. So it's likely that gravel flying around at high speed scoured that off the steel. And if it weren't for those three conditions, it's very unlikely that the steel would have softened. Another thing that I found very painful to hear about is that the people who had gotten to the top of the building, all of our big cities have the capacity to rescue people from the top of the building. The fire was so intense that the updraft prevented helicopters from rescuing those people. And so at that site, more than 2,600 people died. And I would like to make that impossible in my lifetime if I could.
Thank you very much.
Bela Buslik, ACS. The polymers you were talking about initially, the one that's just long and kind of stretched, would there be a possibility of lining fuel tanks and everything else with essentially the thing? So when the thing gets hit and it starts presumably vaporizing, well, stretch out the thing and just confine the thing, because if you can stretch 95%, that's a heck of a lot of space.
It is a really amazing thing. So that's beyond my expertise, but I'd like to let you know that I'm speaking in a symposium on mitigating impact. So if you have the possibility of explosions, fires, simply projectiles penetrating armor, there's a whole symposium dedicated to just that, going on right here. And there are people who are working on very clever strategies for making the material of a fuel tank so that it's much harder to rupture. And there are also people who are working on new kinds of very thin, very lightweight armor that might be able to arm fuel tanks as well as people. So I encourage you to take a look at the other talks in that symposium. It's been very interesting, and there's guys from the Air Force and the Army there. They are super expert in this area. So I would encourage you to come, and I can also give you some of the names.
Thank you.
Yeah. So.
Are there any other questions? Katie?
Sorry.
Katie Cottingham from ACS. So I was wondering, do the vehicles or planes have to be modified in any way to use this fuel, or can you just kind of dump it in with the mega supermolecules in them?
So there are many requirements that go into the performance of fuel in vehicles. In airplanes, they serve as a heat transfer fluid. They also, this is all stuff that I learned from contact through this project. So when you go up to high elevation, the plane is very cold, the wings are cold. So if you land in a place like Florida, you get a lot of water condensation in the fuel tanks. And so it's very important that the water be able to settle out of the fuel. So we were fortunate that an expert in the requirements talked to us at the very, very beginning of this project. And so he said, you have to be able to survive filters, you can't increase the pressure drop through filters, you have to permit dewatering, you can't emulsify water into the fuel. So there's a whole list of criteria that we had to satisfy. And by telling those to us all up front, we were able to take it into account at each step, designing the molecules. So we're cautiously optimistic that it can be a drop-in solution. Don't modify the vehicle, just put in less than 0.1% of the polymer, and it should be relatively invisible to all the systems of the engine and the heat transfer. Yeah.
And how would the cost be? And would it be noticeable at the pump, or would it be kind of negligible?
I would say it would be noticeable. So it would add, so in the US we use gallons, it would add maybe 2 cents a gallon. So people would notice it, but depending on the benefits it brings, people might like it. And there are a few ways in which it might possibly pay for itself. It reduces the energy cost of transporting fuel through pipelines, and that might help offset the cost. That remains to be seen, so hopefully we'll find out over the next couple of years. Yeah.
Any other questions? All right, the archived version of the session will soon be posted at bit.ly/ACSlive_Orlando 2019. Please join us for our next press conference today at 2:30 p.m. on molecular surgery that reshapes tissue with electricity but no incisions. Thank you.